Today, what we will do is that we will cover biodiesel, okay, and with that we should be over with biomass uh, as a resource, and then we will move on to solar energy, okay, and the next few lectures will be on solar energy. Now, just like we found we saw last time that Henry Ford had actually run his vehicle on pure ethanol. There was no blend or anything, and that was a very historic trial that he did. And then after that, of course, Brazil became the pioneers in introducing ethanol in petrol, and today, of course, the whole world, does it. And in India also, we have about 8 to 10% ethanol mixed with gasoline. Okay. Similarly, it was Diesel who basically ran the first. He's the one, of course, as you know, he made the diesel engine. That's why it's after his name, Rudolf Diesel. And the interesting thing is that when Diesel made the engine, he actually ran it with pure vegetable oil. And so almost like Ford, running it with neat ethanol, Diesel also ran it with pure vegetable oil. And what he said is the diesel engine can be fed with vegetable oils and would help considerably in the development of agriculture of the countries which use it. So it was a very visionary thing that he said, because so many countries were dependent on agriculture. Even today, they are. And so obviously it opened a new avenue, a new outlet for vegetable produce, to be actually used in a vehicle. And what I've shown here is the first vehicle, which looks like a rickshaw, which was made by Daimler and Benz in Germany. Okay, and now these are the kinds of things which were being later on run with diesel's engine. Okay, and it was a very important milestone. In fact, I took this picture when I had gone to Stuttgart to the Mercedes-Benz headquarters in Germany. And but now, subsequently, it was not really possible to run these vehicles, like say today's vehicles, with neat vegetable oil, just like Diesel had said. And the reason for that was that there was a transition from low-speed engines, because what Diesel had made was a very low-speed engine, and today what you have is high-speed engines, and in these high-speed engines, the nozzles, through which the fuels are introduced, are so fine, and the vegetable oil viscosity is quite high, and so it becomes very difficult to run these high-speed diesel engines with the vegetable oil, simply because the viscosity is so high. Of course, there are other issues. I'm not going into all of those. And so there was a need for a change. Okay. Now, today, which was not necessarily very relevant, say 100 years back or 130 years back, but today, of course, it's increasingly relevant, as you know, that vehicular emission has caused a lot of pollution in the environment. It's one of the biggest polluters, apart from power plants. And all vehicle companies have been very mindful of the fact that they need to do something about it. Okay, I mean, and this is not now. This has been going on for many decades now, that they have been very concerned. Okay, and and it's also interesting that just very recently, what let's say the United States, Britain, and the European Union have done is that they have set a target of 2050 to reach net zero. Means there will be no net CO2 generation, and by which point they will only emit an amount of greenhouse gases that can be absorbed by forests, crops, soils, and other things, and by carbon capture technologies. Okay, so that's what they've said. That so it's obviously very important. In India, of course, one of the biggest motivations for introducing biofuels like biodiesel would be really that we are so heavily dependent on imports. That's another dimension for us. That it's not a environment is of course an important issue, but if we do not run these things on fossil fuel as of now, then our entire growth pattern will get very badly affected. Okay, so we have, and of course, so we need to look for replacements. Okay, now when one talks about net zero, I thought that it's important that we, have a common understanding. So I've just done it with a Jatropha plantation, like let's say, okay, and so plantation means obviously you are getting some produce. The trees are getting bigger, then they are having some seeds, fruits. Okay, and all of those things will basically assimilate carbon dioxide through photosynthesis. In fact, I asked a question to you all in the last exam, that how much of the solar energy is getting actually captured in the oil. So that's what happens. Okay, and it's not just the oil. One is of course the oil that you get, okay, which will be what will become biodiesel. But then there is a carbon sequestration in well, all the different products which you get. So parts of it will go into your biofuel and things like that, and the rest of it will also have captured quite a bit of CO2. Okay, but they may not directly go into your biodiesel. Okay, but they would be useful products. But some and substances that you would have harnessed CO2. Now, on the other hand, let us look at all the things that will actually produce CO2. Okay, so one is of course if I am making a biofuel, or let's say other parts of the plant which I am burning. So all of those are going to release carbon dioxide. Okay, from their use. Okay. Secondly, there would be, I mean, even in a plant, when the leaves fall, etc., they fall on the ground, but some of it will start rotting, and slowly it will emit carbon dioxide. Okay, so that's another way in which carbon dioxide is emitted. Now there are also many different insects, birds, etc., which come by virtue of the fact that these plants are growing, and their respiration also leads to formation of carbon dioxide. Okay, then you have to apply in your field things like fertilizer, pesticide. Okay, you may require water, which you need a pump. Okay, so all of those, when manufacturing fertilizers and pesticides also will generate carbon dioxide through the manufacturing process. So you need to take a very holistic view, of all the things which are related in some manner with your core objective of, let's say, making biodiesel, and what all CO2 will get emitted, and people don't want to do all these calculations, because most of them will show them in very poor light. Okay, so they tend to bluff. Okay, but it's very, very important. Okay, so this is all things which are releasing CO2. That same CO2, if I can basically, which will go into the atmosphere, if I am using for, let's say, in my plantation, and suppose I can strike a balance, between the two, then of course that's wonderful. Okay, and that would be a good example of what one means, by net zero. Okay, so keep this in mind, that this is what really net zero would be. Okay. You can ask me questions. Huh? Okay, now let me come to what is the modern day biodiesel, which is derived from oils, but is not exactly the oil directly being used. Okay, so let us see what is really what it is. Actually, any triglyceride oil like vegetable oil or animal fat, that's what it looks like, right? This is a triglyceride. And now, so this is of course the feedstock. Now, what one needs to understand is that, as I told you, that the viscosity of the oil tends to be quite high, and because of that, you can't run the engines today directly with that oil. So, this person, Walton, in England, he had recognized that, maybe the problem is the fact that this has got such a high molecular weight, okay, that it's necessary to break it up into smaller molecules. Okay, and so what you have is, like, obviously these are the ester groups, the triglyceride, this is the glycerol portion. Okay, and these are your fatty acids, which are forming three ester linkages. Now, what he said is that, look, I mean, if we could somehow split, this fatty acid, so that I only get the triglyceride, so that I only get the fatty acid, so I'll end up getting 3 moles of this fatty acid, okay, RCO2H, and what he thought is that, these are quite small, so maybe it will be easier to run the vehicles, with this kind of fatty acid. Now, you do not actually exactly run it with the fatty acid. Today, you run it with the fatty acid methyl ester. The fatty acids are not suitable for putting in the engine, which means that you just have to make you have to split it up, get the fatty acid, and you can then make an ester, okay, like a methyl ester or an ethyl ester or some ester, okay, and glycerol would be your byproduct, okay, from this process. Now, the interesting thing is that, he did not do any experiments, he just conceptualized, okay, and he said that to get the utmost value from vegetable oils as fuel, it is academically necessary to split up the triglycerides and to run on the residual fatty acid. So, and the reason why I thought that is, as I told you, because it will now become a smaller molecule. Now, remember, in oils, the R group, the fatty acid, the hydrocarbon chain, typically has a chain length somewhere between C12 in coconut oil, for example, to something like C18, like oleic acid. Okay, there are some which are still higher, but majority of the things will be around C12 to C18. Okay, and what everybody knew was that when we talk about diesel, basically the ideal diesel is effectively a C16 hydrocarbon, So in a way, these chains, these R groups more or less have the same chain length as diesel, So this is the reason why Walton had basically said that, maybe if we can split it up, because he must have recognized that these R groups have similar chain length as diesel. Okay, and that's why he said that. Now, what is also very interesting to note is that the technology that we really use, like let's say in doing a transesterification, is a age-old technology. It's not new. In fact, it's you can see 1853. In other words, the transesterification was known even before the diesel engine was born. Okay, so there's nothing special about the chemistry. It's just that Walton was smart enough to realize that these individual chains might be suitable as a fuel. Okay, now the first patent, it's a Belgian patent which was granted in 1937. Uh, that is really the one which, for the first time, describes the production of these kind of fatty acid esters on which actually vehicles were run. Okay, and they had used palm oil, which has got a chain length of about C16. Okay, and so very similar to diesel, and they made this kind of an ester. And look, in 1938 they actually ran a bus, you know on that diesel. So we are talking about what, more than 80 years ago, that this experiment, not eight, yeah, so about 80 years ago, that this experiment was done. But then it was an experiment and they just left it at that. And then, of course, the South Africans who are South Africans are very well known for some technologies that they have developed. Probably they are most famous because they are the ones who did the first heart transplant. Christian Bernard, who was a South African, and likewise, some of the best technologies on liquefaction of coal and getting all kinds of chemicals out of coal. The South Africans have been pioneers. The South Africans are pioneers in sugar technology, for example, explosives. So they've really got some amazing technologies that they have developed, even though you don't hear that much about them. So the South Africans actually, what they did was that, they started looking at the technology that was developed in Belgium, and they realized that there are certain shortcomings of this particular product, and most importantly that there were some impurities, etc., which were completely destroying the performance of the engines, and so they studied that in minute detail, and effectively, I will say their best contribution was that they developed a good technology for refining the biodiesels, so that it became more engine worthy. Okay, that's really what the South Africans did. Okay, later on, there was an Austrian company, Gascox. They actually licensed the technology from South Africa and put up the first actually plant, commercial scale plant, of about 30,000 tons capacity, and that was when 1987, not so far back. We are talking about less than 40 years ago. That they put up this plant, and because Europe are very big in rapeseed, so effectively they use rapeseed as a feedstock, and then made 30,000 tons of biodiesel. Okay, but remember that rapeseed is an edible seed, so you get edible oil from it. So even from that time, people were a bit concerned, about using edible oils to make fuel. But nonetheless, I think that this was a very historic experiment. Okay. Later on, you can say 2003. So again, not so far back, but even at that time, Europe had exceeded 1 million tons of biodiesel production. So they moved well, whereas the Americans were just catching up. They were actually laggards. They were not the pioneers, in biodiesel, but they did do some production, but nothing like the Europeans were. So it was really biodiesel was led by the Europeans, and because it was the Europeans, so the European car companies, were most active in this area. Okay, so companies like Volkswagen, Mercedes-Benz, etc. Now, we were very, very fortunate, and it happened through basically one of the professors in Germany who had visited our institute in CSIR, and he went and told about our work on basically on agriculture to these people in Mercedes-Benz, and then they got interested in working with us. Okay, and what that did was it was a very historic project, which started in 2003, although we began talking maybe in 2001 with them, but 2003 we signed a project, with them, and for the first time in the world, what was done by Mercedes was that they were able to demonstrate the use of neat Jatropha biodiesel. Neat means 100%. All these experiments were all these trials, biodiesel, 1.4 million tons and all. These were all 10% blends. Okay, nobody used neat biodiesel, because people thought that it can never run a car, the neat biodiesel. Okay, but the biodiesel that we had made was capable of doing that, and not only that, there was a view that if you do it, then you have to modify the diesel engine. But Mercedes showed that no, you don't even have to do that, and it can run on a direct unmodified diesel engine. So you can literally pour it into any vehicle with a diesel engine, and it will run beautifully. Okay, and but that was really not the only important thing. Mercedes were more interested because this particular plant, there was a potential of growing this plant on very marginal lands like wasteland. Okay, and so there was a very conscious view right from the beginning, and especially because of the experience in Europe, that what one should try and do is that not interfere with the food chain at all, and try to make the biodiesel from oils which are non-edible oils. One is it should be non-edible oils, and the second is ideally they should be grown in land where nothing else will grow. I mean, that was basically very important. Now, following up on that 2004 very historic work, was another historic work done in 2008, and I think I mentioned about it, that Air New Zealand, basically, this became so popular, this Jatropha, that they then ran a Boeing 747, okay, as a 50-50 blend with a biodiesel made from Jatropha oil. But let me tell you that this biodiesel is very different from this biodiesel. Okay, this biodiesel is this. Okay, this is a bit different, and I'll tell you later on what is that kind of biodiesel. Okay. Now, as I told you, I mean, the biggest interest, was that we were trying to actually grow all kinds of different potentially commercially important plants, try to grow them in very, very difficult to cultivate lands, and what we call barren lands or wasteland. Okay, like you can see, like this is how the land was. It's absolutely dry. It's like rocks. Very difficult. to work in this land. And that's what was transformed by the people who were working with me. They were able to, grow these Jatropha plants there. Okay, and so this is what really attracted the attention of the world. And in fact, maybe I'll send you a an article which was published in Nature by this person, effectively centered around all of this work. So maybe I'll send it to you. Okay. Now, before I come to this, so since I mentioned to you about this, now there is I mean, I've not taken the whole film. I've just taken a snippet from the film. Okay, it was made by German television channel ZDF. Okay, and so there were people from Germany who had come and filmed this work of ours. Okay, and so I'll just play it. It's just about 2-3 minutes. Okay, so I'll just play, and later on I'll describe to you some of these things. Okay, so you would have got some idea about how exactly. I thought I'll cover all the way from how the plants look. I mean, how they grow, the fruits, the seeds, and how biodiesel is made, and how it was running a bus on 100% biodiesel, just so that you can see the entire chain, okay, of how this is all done. Later on, I'll describe to you in more detail the individual steps. Okay, is it clear to everyone? All of you are understanding? You are able to see everything?
Yes, sir.
Okay. Okay. Okay, now, I told you that it is run on 100% biodiesel, but actually, there was a very stringent kind of a specification, okay, of the fuel, right, which we had to effectively first comply with, because till we had achieved this, nobody would put it in their car. Mercedes would not put it in their cars unless we had been able to achieve this minimum specification. Okay, and this is, of course, what the actual results were. And what was important was that in almost everything, not only did it match the specifications, but it far exceeded the specifications. Okay, and it was because of that that they had the confidence of trying this historic run with neat biodiesel without modifying the engine. Now, another very interesting thing, I mean, which nobody talks about, but which became very clear to us, is that it's amazing that this particular fuel has a flash point of about 100 and what, about 140 50 degree centigrade, so it cannot accidentally catch fire, and so in fact this was another thing that we learned, when people were trying to take a license from the Petroleum and Fuels Act and all. They said it falls outside the Petroleum Act because its flashpoint is so high. Okay, so that was very interesting. So this neat running was also gave us this very interesting thing that you could basically run in a way that accidental fire would be almost negligible, in this kind of a situation. Okay, and all of this analysis, most of it, except for a few, were generated in Germany by Mercedes-Benz. All this analysis, we did not have the capability of really generating any of this. Before again, this was put into a vehicle, there were a lot of test runs that were done, on test engines. Okay, and that was done in Pune by the Daimler Chrysler India and Automobile Research Association of India, which is also in Pune. So they had really done these testing, and so they tested both for fuel consumption in their engines, and also they looked at all the emissions, CO, hydrocarbon, NOx, particulates, CO2, so all of this was actually looked at. Now this methyl ester that I told you about, you can actually do esterification. For those who are familiar with chemistry, you can do it either using a base catalysis or an acid catalysis. Okay, and so both kinds of catalysis were done. Okay, and both products actually passed the test. I mean, they were very good. Okay, there was no problem. But finally, the base catalysis was chosen because it was a bit simpler to carry out this process. For one thing, it could be carried out at room temperature, and and there was a few other advantages. But so effectively, this is what was selected: the biodiesel-based catalysis. Okay. Now, this is that run that I was telling you. You can see April 5, 2004. Merck to run on pure biodiesel, and so this was the first time in the world. So this was the first experiment like this anywhere in the world. Okay, and then they ran, I think, about two cars. One went to the from Pune. It went all the way to Delhi. Of course, coming to our place and picking up the all the extra biodiesel that they required and things like that. And so this was the thing, and then another was in the southern part of India. And the results were absolutely as per expectation. They got even more daring, and in the next year, 2005, uh, they did something unbelievable. That They went to Leh, to the highest motorable road in the world at something like 18,400 feet. Okay, and they took three Mercedes-Benz cars. You can see these Mercedes-Benz. Okay, three of these to Leh, and I was also there. And So, I mean, the vehicles, even in that rarefied atmosphere, the vehicles actually ran well, and we have a understanding of why they ran so well, and all the emission data, etc., was generated, and basically, I think that what was at that time, the specification of fuel was Euro 3, EU 3. Okay, and it far exceeded EU3 specifications. Okay, and then I told you about Austria, because Austria had the best bio diesel institute in the world. And So the Austrians actually did another study where they compared this Jatropha biodiesel with biodiesel from Europe and some other parts of the world, and effectively, it came out right on top. This is standard diesel. Okay, standard diesel. When I say this is not what you get in the petrol pump, it's a special kind of diesel against which it's compared. And then after that, this was the result. And what it was measuring was really the output, the torque, from the engine, 16 days of continuous running of the engine. Okay, and you can see JAME, that is the Jatropha methyl ester, this one. Okay, and so it came out right on top, and because it was the world's best biodiesel, so that's the reason why I will share with you the details of how exactly it was made. It was so good that that there was a thought at one point to actually there was going to be a race, like Formula One and that kind of, not a Formula One race, but another race, and where actually they wanted to put our fuel. It was from Paris to Dakar in Africa, and 5,000 kilometers. Yeah, but I think it finally never happened, this race. Okay, but it was all set, to run. Now, and similarly, this is what basically was running all the vehicles in our country on biodiesel, starting from in Gir, the buses in Gir, Forest, DRDO, all the military vehicles, they had licensed the technology from us, and another company in Rajasthan State Mines and Minerals. So it became a very interesting technology. In fact, there was this sheikh, he's the crown prince of one of the Emirates, Russell Khaima. Okay. He came all the way to our institute because he had heard so much about it, and actually witnessed everything, how it works, and things like that. So obviously this is all and all over the world. All these Mercedes-Benz cars running on this stuff and things. So what is important is that it looks like a surprisingly simple technology. You can imagine there's only an oil and there's a you need some methanol for the transesterification, and there is a base catalyst like KOH or some catalyst like that. Okay, and then you are forming the methyl ester and this. But it looks so simple, but most people could not get it right. Okay, and I'll tell you what were some of the complexities. And sometimes don't get fooled by these simple equations. When you actually go to do something, you'll realize how difficult a so-called seemingly simple problem sometimes can be. That the whole world is trying to do it and they can't do it. Yeah. So now, and just to show you, that biodiesel is, if we could actually grow and run vehicles on biodiesel, it would be unbelievable. Like this was, the engine of this vehicle, this one, okay, was opened up after about 163,000 kilometers of running on 100% biodiesel. And these Toyota yeah, mechanics were absolutely amazed because the engine looked almost like new. And finally, of course, it covered about, I think, about 2.2 kilometers, and maybe at that point the car became too old. Okay, and but the engine was almost like new. Now, it's not just about running vehicles. Actually, you can run stationary engines also. Okay, with this. So, in fact, at one time, all these stationary engines from our country were getting exported a lot on the back of this performance. It was an outstanding performance, and you could even do very, very big vehicles like earth moving equipment, and things like that. All right, they were absolutely everything worked fine. So obviously, it was, and all of this was. I think I'm not sure about this, but all of this was 100% biodiesel. Now, it's not only that one was using Jatropha oil. Another thing around that time, and in fact, this kind of work was going on in the US for quite some time. People like McDonald's, because they make so much of French fries and all, so they have a lot of waste oil, and so they were trying to make biodiesel from waste cooking oil, and you can see from this email, we are talking about 2006, okay, when we were actually working with Pepsi at that time for something, and then because they make all these Frito-Lay chips, so I said that why don't you send us some of your waste frying oil, and let's convert it into biodiesel, because that's also a good thing, because otherwise if you keep frying in the same oil, it's not good for your health. So if you have a good outlet, like you use it for frying, etc., as long as you want to. After that, so that the oil doesn't get too bad and it's good for your health. Okay, and after that, just convert it into biodiesel. So this could be a huge resource, and you can see it. They were of course not very sure about how much waste oil they have. So they wrote that we don't generate much waste oil and will work with our suppliers of oil to determine their wastage. If quantities are interesting, will champion implementation. So obviously, I mean, this is something that had captivated people across all things. Now, another thing that you must remember is, when you are developing technology, okay, you can see 2006, right? The technology was developed in 2004, okay, and it takes sometimes a long time before something actually sees light of day. Okay? And the reason is because most of the time people are waiting for somebody else to do something. They are not so confident about technology. They don't have initiative. The general tendency is to maintain status quo. You know, that's what people do, and it's strange. It's I was just seeing 2019. Okay, used oil to biofuel. 2019. 15 years after the work on biodiesel was done, and look at this. This is also bizarre. Government and Austrian firm. Who knows? The guys in Austria we were working with. Maybe the pinch collar technology. It's strange. The whole thing. So this is another thing about technology development, etc. That many times what you'll find is the pioneers, get shortchanged, okay, and somebody else makes the money, not the people who actually did the work, okay. Uh, okay, so as I told you, I mean the engines, etc., were all found to be very very clean, and I showed you the specifications of biodiesel. So let me now come to actually how this biodiesel is made. Okay, uh, and a little more of the details. And frankly, I mean, any of you can go and do it. We made the technology surprisingly simple because actually our interest was really to put up many such plants all across villages in India. That was the plan. But I'm not very sure that it took off. Okay. Um, so this is what you saw in the video. Okay. So in the video, you saw those women plucking the fruits. Okay, from the plant. Okay, and then this particular machine, you saw a machine. What that machine does is that it removes the outer shell, the capsule, and then you get these seeds. Okay, this is the seeds, and those were the seeds which were going into this oil press. Okay, the seeds. Okay, and then the oil that you got from that, of course, a bit of the method of manufacturing biodiesel was shown, but I'll tell you a bit more of the details. And then the cake, that you get, okay, from the oil cake after pressing and getting the cake. The cake is an excellent manure, so you can just put it back into the field. So ideally, what one should do is do this part of the operation within the field itself. Within the field, when I say, maybe you could have something like 300 to 500 hectares of cultivation, and around there you put up one oil mill, so that you're not having to transport things over long distances. Okay, and also what was found is that when you keep the seeds stored inside the capsule, that means don't take it out, till you are actually ready to use it. You can, and at that time, if you take it and do this, what you find is that the seeds, the oil, has much less of free fatty acid, and it's a much better quality oil. Okay. Now, when you get this cake from the oil cake, and you get the oil for your biodiesel, there will be some sludge type of material. It'll always be there. Some and you cannot really make biodiesel from that, and nor can you put it into the field. A good use of that was to take this kind of shells, these shells, and you can use that sludge. It's a very good binder, and you can actually brick it. Okay, you can make briquettes. Okay, of this, and then you can actually, like we saw, biomass gasifier. Like you can put it into a gasifier and generate power, or you can generate thermal energy, whatever you want. Okay. Uh, Now, and the cake which I showed you, not just for Jatropha, but it has been used for many other crops. and it grows very well. These are trials on cotton, bajra, and these trials are all done by professional people at very large scale. Okay, so these are not very small scale experiments. Okay, now let me come to the making of the biodiesel. So you saw how the oil was expelled. Okay, and so this was the seed, and from which you get oil. Now, some of the very important things, as I told you, is that any oil will have some amount of free fatty acid, okay, and this is very detrimental to in biodiesel. And secondly, if these are present in your in the final biodiesel, I mean, if you can't remove it, then it can really cause havoc in the engine. And actually, in the actual biodiesel which you get, see over here it's 2.6%, but when we finally look at the free fatty acid in biodiesel, it's just about 0.29%. So that means almost 90% of it has got removed. Okay, and that's the first thing that one needs to do. One thing that I did not mention, but I should have, uh, like uh, there are two reasons why this why the Jatropha biodiesel particularly work so well. One is really that we had a very good technology, okay, which we had developed, which I'll describe to you now. The second is that the the fatty acid composition in the biodiesel was very good. That means the Jatropha oil fatty acid composition is quite ideal for making biodiesel. And that's what we learned. I mean, that it's really very good. That's one. Second, Jatropha oil is one of the very few oils which does not have any phospholipids. Okay, and because phospholipids are very detrimental to the engine, and I think there is a specification for, yeah, you can see phosphorus content, should be less than, they had said 4, and in our case it was less than 1. The reason is because the Jatropha oil did not have any phosphorus, so this was another very, very important thing. And to that extent, sometimes what looks like a problem can sometimes be actually a good thing. Like use cooking oil. Now, when people make cooking oil, one of the refining things is that you remove phospholipids from the oil, you know, in making any of these cooking oils. So it's not there. So to that extent, the Jatropha oil and this used cooking oil had certain things which were common. Okay, and so bear that in mind. So there is selecting the right kind of oil is also important. Although we have made it with many different types of oil, I mean, you just have to have slightly better refining methods for the oil before you actually make the biodiesel. Okay, uh, but that refining is almost negligible in the case of Jatropha biodiesel. Okay. So first thing, as I told you, you've got the oil, and it's got uh, uh, even though this free fatty acid amount is not so high, but you still need to get rid of it. Okay. So what was done? By the way, all of this is patented. This entire thing, and this is the patent that has been granted to us. So this is all covered by granted patents. Okay. So the first thing is that, and this is all part of the inventions, which went into actually making this product. Okay. What you do is that one takes uh, alkali, sodium hydroxide, okay, but one you have to control several things. You have to control the concentration of the sodium hydroxide solution, the amount of the sodium hydroxide that you actually take, okay, and also the temperature at which you are taking this, okay. And so that what happens is that it's done in a way that the sodium hydroxide only neutralizes the free fatty acid without saponifying the oil. Okay, because the alkali can also saponify oil. That's how you make soap. Okay, so we must not make any soap, because if you make soap you lose material, okay, and also it will worsen the quality of your product. Okay, so that is the first thing, that one neutralizes it. Okay, and then you get a soap cake, okay, after the neutralization, and every gram of this seed has been utilized in some product. Okay, so like for example you can see this soap cake, plus there is some other source of soap, all of that mix gives you this soap. Okay, this soap. So like in a village, you can actually use every product that you can make, and it doesn't mean that just because you are focused on biodiesel you have to only make biodiesel. You must think about all the secondary biomass, which we learned, isn't it? All the byproducts that you get when you are processing it for your desired product. Okay, all the secondary biomass. So that's the first. Now, after that, what one does is that you try to make the moisture content in the remaining oil. And to remove the soap cake, it was taken through a continuous centrifuge. Okay, so the soap cake comes out, and you get a oil, which is now free of the fatty acid. Okay. All right. And then one sparges the oil, with dry air, and you try to remove as much as the moisture as possible. The reason for that is that presence of moisture can lead to saponification when you are doing the next reaction. And so you need to try and reduce the moisture to the maximum extent possible. Okay. And also when you're doing that, try not to put anything from outside. Like that's why we sparge with dry air. We don't add a desiccating agent. Okay, and nor do we do a vacuum heating, because again it means that you have to have heat. So all of these are room temperature processes. Okay. Hmm. Now, then what one does is that for the transesterification, okay, the oil, you take methanol, and methanol has to be taken. Obviously, you need 3 moles of methanol for 1 mole of oil, because there are 3 fatty acid chains. Okay, but typically what you have to do is take about 1.5 times that amount. There are people who take 5-6 times that amount. But in this particular technology that I'm talking about, you just take about 1.5 times that, and the base catalysis is required. So we use potassium hydroxide. The reason for using potassium hydroxide is that later on we convert this into a fertilizer. Okay, so I'll tell you how that is done. Yeah. So basically the methanol and the potassium hydroxide are fed, and you can see these are this is a 83 kg of oil. So I'm talking about fairly large scale process. Okay, I'm not talking about a laboratory process. So any of you can go and actually practice it. Now, another thing that I didn't mention, that when we do the neutralization here, many of the color and other junky stuff which is present in the oil, all of it seems to come out along with the cake. So so the oil becomes actually like golden yellow, beautiful color. Okay, and then when you do the reaction, you'll get glycerol, and along with the glycerol, what you also get is some amount of the unreacted methanol, and the potassium hydroxide, not all of it, but some of it, which comes out. Normally, one reaction was enough for us, but if you're not doing it carefully, then you might have to do it a second time. Okay, but frankly, in our case, it was one of this reaction was good enough to make the final product. Okay. Now, what happened was that even after when we did the reaction, there was still quite a bit of impurities which were still present in the biodiesel. For example, there was some methanol. There was some catalyst. Okay, some amount of saponification invariably happened. Okay, and those things were all sitting with the oil, and 100% of those impurities did not come out over here, although the majority of it came out. So some amount was still remaining with the biodiesel. Okay. Now this is where we had probably the most uh, inventive step, the innovative step. What we realized is that this glycerol which is formed when one makes biodiesel, that the methyl ester, it takes most of the impurities, but as I told you, not 100%. And what we realized is that the reason why it can't take 100% is because the amount of glycerol is limiting. Glycerol is formed roughly to the tune of about 10% by weight of the oil that you put in. And we realized that you need more glycerol if you want to take out all of this. Now, is there any other way to remove impurities? What would you have done if there was impurities in your biodiesel? Biodiesel, of course, does not dissolve in water. What would you do? And you had catalyst, KOH, some methanol, and maybe some soap, saponified products. And also, sometimes, what happens is the entire, you don't get always glycerol coming out. Sometimes what will happen is only two of the fatty acid chains will fall off, or sometimes one. So you'll end up getting a monoglyceride, a diglyceride. These kinds of things can also form, and they're very detrimental. Okay, so we had to get rid of all that. So how would you get rid of it? What would you do if you suppose you had KOH, methanol, etc. Present in your biodiesel? What would you do to purify?
Some adsorbent, sir.
Adsorbent. That's a good idea. Adsorbent. Yeah, it's a good idea. Now, one of the other things. Let me tell you that you know you have to make sure that there is absolutely no particulate matter in your biodiesel. And sometimes when you are using adsorbents and all, by because of attrition, some amount of these particulate matters and sometimes very fine material can go into your biodiesel. Okay, but it's a good idea. I think you've given one example. Let's put it down. How can you clean up the crude biodiesel? Okay, this is the question, and I'll say student use adsorbents. Okay, that's one. But remember that there are many different kinds of impurities. Okay, so you'll have to have an adsorbent which can deal with all of those. That's just keep that in mind. But it's not a bad idea. Anything else? Just the simplest thing that you can possibly do. Can you put water?
Washing.
Yeah, I'm just saying because you have got KOH, methanol, etc. They're all soluble in water. Hmm. So do you think we can put water for washing?
Maybe, sir, but there might be a chance of emulsification too.
Very good, very good. You can wash with water, but there is a chance of emulsification. Right? That's what you said. Huh? Correct? Have I got it right? Is that what you're trying to say?
Yes, sir.
Okay, great. Very nice. Uh, Now, exactly that happens, whatever you said. Uh, the most common thing and which till or patent everybody was doing was that they were trying to add water. But then it forms emulsification because what you have got water, you have got oil, you have got alkali, so and there'll be some unreacted oil, so it can saponify and form a soap. So you have got soap, you have got oil, you have got water, you have got the perfect recipe for an emulsion, you know and that emulsion is so stiff. Okay, it's virtually impossible to break it in reasonable time, and so you require long periods of standing, okay, to be able to break that immersion. And I believe that that was the reason why nobody was getting it right. And although it sounds simple, as I showed you the equation, oil plus catalyst plus methanol make this, but in reality it's a horrendously complicated problem. Okay, so the invention was that uh, actually in any case, some of this glycerol finally is recovered, okay, as pure glycerol. Okay, so what one does is that you again add glycerol into the crude mixture after you have removed most of it, and you can give like one or two such washes with glycerol. you know. And glycerol, what it does is it removes everything from the biodiesel, okay, and it just depends on how much glycerol you are adding, okay. It removes everything, and so all of these glycerol washing you'll get, okay, not a big amount. Okay? After that, what you do is that when there is virtually nothing there in the biodiesel, okay, at that point you wash with water, just so that if there are traces of glycerol and other things, they can be removed in the water. Now, when you wash and it comes out, there is no emulsion formation. It will give you two clean layers, easy to separate. Okay, so you take out everything, okay, and this biodiesel now, because you have added water, is wet. Okay. There will be biodiesel, because of the methyl ester, has some amount of moisture affinity, and so and if you put that in your car, your car engine will corrode, so you need to remove moisture, traces of moisture. So how would you remove the traces of moisture? And you have to bring it down to something like less than 500 ppm, or maybe 200 ppm, or something like that.
So, by freezing it, maybe, sir.
By
Freezing or drying, sir, or heating.
heating means heat and apply a vacuum or something.
No, sir. Some temperature at which the no, not exactly heating, sir. Like dry air or something, sir.
Very good. In fact, in that film, you would have seen, okay, you would have seen that, towards the end, there was biodiesel in a trough, okay, and there was a lot of air being spurged through it, okay, and that was really to get rid of the moisture. And you can do it with biodiesel, but you won't be able to do that with gasoline, simply because gasoline has such a low boiling point. But biodiesel has a very high boiling point, you know, something like 300 degrees centigrade. Okay, so it's very simple to sparge dry air, and you just carry all the moisture with it. Okay, and so that's what it says here. Okay, dry air, right? And you take out the water vapor with that. Okay, and you can see the moisture content. It's about 450 ppm, which was within the specification. Okay, and you'll also see that starting from around 83 kg, of the oil, after you have removed the uh, free fatty acid, you get about 78 kg of the final product. So you are talking about very high. In fact, this was slightly lower, but typically about, say, comfortably about 95% conversion. You can get 95 to maybe 97%, is what you can get. And now, when you get these stuff, okay, over here I showed you how you get soap cake. Now you can neutralize the alkali with, let's say, sulfuric acid. Firstly, what you do is you do a vacuum distillation of this layer and pull out the methanol, which you can recycle. Okay? It's because the volume is very less, you know. So you can take out the methanol, okay, and then what you can do is add sulfuric acid, not solution necessarily. You can even add concentrated sulfuric acid, okay, and it will form potassium sulfate, which is a wonderful fertilizer. Potash, sulfate of potash. So you'll get this kind of a fertilizer coming out of this, and then the crude glycerine, okay, part of it you can distill because you need it for this step, but we also found ways of utilizing the crude glycerine.
So what was the cost for the Jatropha biodiesel, sir?
But I can tell you that at that point in time, it was around 65 rupees per liter. Okay.
Okay, sir.
And at that time, the cost of diesel was around 48 rupees per liter. I can also tell you that. Okay. Uh, so now, this is what was done with the crude glycerine. See, it looks like this horrible stuff. Okay, and basically what we succeeded in doing is converting it into bioplastic. Okay, and the particular microbes that we required for this, she's a microbiologist, Dr. Sandhya Mishra, and when I asked her to look for this possibility, she went and searched the all over and was able to find ideal microbes, some marine bacteria, which she went and found from the Arabian Sea, and that's what was used for producing this bioplastic. Okay? And it was a big enough invention that it won the CPET National Award. You can see the country became famous, not just for making biodiesel, but India develops plastics from the Jatropha plant. I mean, so every bit of the fruit, okay, was completely utilized in making useful products. Is everybody clear about the process now? Any questions on any part? In maybe I'll pass on the patent to you, and all these patents and all you can have a look at. So also how exactly one monitors, what is really the criteria of whether you have developed a attractive process or not. So all the parameters are given here, but one of the very important is that 75% of the cell weight of that bacteria was the plastic. you know. Okay, I mean, so that was very impressive that the bacteria produced so much and assimilated so much of this or accumulated it in its cell. Uh, One of the problems is, of course, that you have to then destroy the bacteria to take out the plastic. I wish there was a better technology to do that. Okay, but anyway, I mean, these are some of the indicators of and the parameters, okay, which you might want to look at. Right? Is it clear? You understood, no? What all we take? We take the crude glycerol. We also take the hydrolysis because we need a protein source, nitrogen source. So that comes from the oil cake. We hydrolyze it. We control the pH, okay, and and really don't little bit of some medium has to be introduced, okay, and the incubation time is quite long, 96 hours, right? And then and overall roughly about the about 20% of the total carbon which was there in this in the oil cake and crude glycerol, roughly about 20% ended up as plastic. So, I mean, it's not 100%. Of course, in any case, 50% will go by respiration, but it's not a 100% conversion. All right. So I'll send you the patent so that you can read, and also it will be important so that you know that when you're writing a patent and people ask you what exactly is your invention, that are you able to clearly bring out, the inventive steps in whatever you have done? Because if you can't bring out the inventive steps, then you can't get a patent. Okay. And one of the things, like for example, it was so important, this neutralization, to remove the phospholipids and free fatty acid and all right in the beginning, before starting the transesterification, that a very detailed study was done subsequently, and we could correlate, that how well we do this step, we could correlate with how frequently we need to change the filter, the oil filter. And so it was just incredible. I mean, when we could correlate it exactly with the free fatty acid content, and so we knew, that this is what these are all the reasons why those vehicles, etc., were running so nicely. Okay. Uh, and anyway, I'll go through this. I'll not go through it. Okay. Now, up till now, I've only told you about downstream. Okay, which is how to make biodiesel from the oil, or from the seed. Okay, but the biggest challenge and the reason why India has not made that much of headway is that we did not really succeed. Maybe a few people did, but the majority did not apply their mind on the agriculture part, of how to raise the crop. And that's very important. And secondly, because the crop, the focus was to raise it on wasteland. Is not so easy to raise something on wasteland, barren land. Okay, so but that was set as the success criteria. If you can do it, well and good. Now, before I go to that, let me tell you that uh, why, for example, this work was taken up in the first place, right? Because the institute where I was the director, and one of the things, which this institute was trying to do was trying to grow important crops in the most difficult places. Okay, like for example, we were we are very big in desalination, in making salt and marine chemicals. So the cost was always of importance. So in fact, one of the things, for example, these plants, this is, you might have heard of jojoba cultivation. If some of you use these fancy creams and things like that, you'll find contains jojoba oil, and this plant, it grows in the desert, and this is all sand dune, what you see. So these plants are actually growing in the sand dune, and it gives an oil, which is extremely good for the skin. It's also a very good lubricant, and so all that's the reason why all these personal care products now, have started having jojoba oil, and this was introduced in our country by some of my colleagues, in the 60s and 70s. They got it from originally from Israel, and did the first cultivation outside of Israel in our country. Okay, this is another case, where this is, you can see the sea coast, the sea, and this is all saline water, and this kind of vegetation grows with seawater, you know. And these were the kinds of activities that they were engaged in. So it is because of this that the one of the committees of the United Nations, had asked us that whether we can look at the possibility of growing Jatropha plants on wasteland. Okay, and that's the origin. Okay, because of all this work that was done, and the kind of thinking, that the United Nations, I think it was United Nations Environmental Program, that they had thought of. And I'm talking about around 95, 96, and without that, we would never have been able to actually take up this kind of a project. Okay? So under that, then what my colleagues did is that they searched all over India, looking for plants which are quite productive, okay, where you see good fruits of Jatropha, okay, and then they identified some plants like that, okay, where the seed yield was quite good, and then they developed technologies initially of tissue culture and later on of vegetative cuttings, okay, and from those maybe 4 or 5 plants, okay, they raised hundreds of hectares of these plantations, okay, from those cuttings. Right? So they were like quality germplasm, right? And this is what gave us good productivity. Okay, and so you can see, like if you have a really productive plant, that you can see how nicely fruit bearing they are. And the point is that only 1 or 2 plants can be like that. All your plants need to be like productive like this. And so although I showed you about biodiesel and all, let me tell you, 85% of the effort was in agriculture, was in plant biology, all that kind of activity. I mean, and so that's how the best germplasm was identified. And even while growing them in wasteland, when we compared with typical yields of oilseed crops, things like zea maize, brassica, others, okay, we were not doing so badly. It was not too bad. Okay, these yields of 1,300 kilogram per hectare actually compared reasonably with some of this. So it is possible if you apply your mind properly to grow these things. Okay. Now, after all that, another thing that you must keep in mind whenever you're working on bio fuels, right, is you must do a carbon or an energy balance. How much energy are you investing in whatever you're doing? Like, for example, we might be requiring heat somewhere, you might be requiring pumps, you might be requiring fertilizer. All of those things actually consume energy, because finally, what are you trying to make? You are again trying to make a fuel which is giving you energy. Of course, maybe it's a fuel for a more fancy application like driving a car, but nonetheless, it is a energy fuel. Okay, so this is the way in which one looks at it. What you do is that you start looking, and I can share with you. I don't know if I've got it. If I've got the Excel sheet, maybe I'll share it with you. So you have to start looking at what are all the inputs, okay, and what are the outputs. So in our case, what were the outputs? Well, we got those fruits, then we removed the seed, okay, and the shell. I told you that we took the sludge and the shell and we made briquettes out of it. Okay, so we knew what is the calorific value of those briquettes, okay, and how much briquette we can produce, from let's say whatever tons of bases that we had. Okay, so we worked out, this is the energy output from briquettes. Then we made biodiesel. We made about for whatever I think it was for yeah, it was for 1 ton of dry fruit. So from 1 ton of dry fruit we got 0.14 tons of biodiesel. So from the calorific value, we could work out, okay, that the energy in this biodiesel is so much megajoule per ton. Okay. Uh, Now the oil cake, we were putting it back into the field. I showed you. Okay, so I can't take anything. Yeah, because it is again getting recycled. So that's why it's been left blank. Okay, and now on this side, what all do I require? We had to work out how much manpower did we require. Every manpower, there are calculations that a manpower is equivalent to how much energy. Okay, and so from that we had to put how many megajoules of energy was being expended by human labor. We did irrigation. So we were operating pumps, right, somewhere, or maybe a few other things I don't remember. But so we had to put that in. You read fertilizer. So what are the fertilizers that you required and how much? And to produce those fertilizers, how much energy was consumed? Like how much energy was consumed in making urea? How much energy was consumed in making diammonium phosphate? Okay, things like that. Right? So you put that in. Pesticides, did you have to apply pesticides, and then how much energy was required? There were transportation related costs because you have to move things, so you add it up. How much power did we consume? Was there any, because we this was done where some of the power is actually derived from our products itself, so we did not actually require any external power. Okay, but then you add it up, okay, and you can see it's 1684 megajoule per ton of seed and of fruit, sorry, not seed, and this is the total energy in your two products, your briquette and your biodiesel. Now what you do is that if you want to do an energy balance, you just divide output by input. So 8348 divided by 1684. Can someone divide and see if it comes to 5.07? 8348 divided by 1684.
So comes near 4.97. 97.
4.97.
Yes,
Okay,
sir.
okay. So maybe there was a slight, but you can see it's roughly equal to 5.07. Maybe there was some calculation mistake. Okay, but roughly. So this is a very attractive number. Okay, so if you are ever interested in making producing biofuels, okay, then this is the way in which you should be doing the calculations. Is that clear? Have you understood the calculations?
Yes, sir.
And by the way, this is the kind of life cycle analysis which you need to do. That is, you cannot just start with your plantation and say, assume that, yeah, I've bought fertilizer and all. You'll have to figure out where that fertilizer came from, how much energy did it require, and look at the whole thing, and then only you can say whether you are going to actually be you'll have a positive balance or not. And the balance is very simple: the energy output divided by the energy input. That's it. Okay, all clear? All clear?
Yes, sir.
All clear? All clear?
Yes, sir.
Okay. All right. Now, in fact, this is another thing that when you are working on biofuels, or for that matter, in anything, after this we'll be talking about solar energy. Same thing will apply there. Never put all your eggs in one basket. Don't be so obsessed with ethanol, or biogas. You say, yeah, everything is required. I need biogas, I need ethanol, I need biodiesel, you know. Okay. And likewise, biomass. Just imagine, okay, if your sole focus is sugarcane. In fact, at this moment while I'm talking, my entire team, there are people who are actually in a biorefinery where they're doing work, they're demonstrating a technology there. Okay. But I was just thinking that if all our focus was only on sugarcane, what a stupid thing. Okay? So you must all, like I showed you, how one could actually cultivate seaweeds, okay, and those could give you ethanol. And then, of course, you have lignocellulosic biomass, rotten crops, etc. So there are so many different types of possibilities. Okay. Likewise, even for biodiesel, it need not only be vegetable oil, okay, or animal fat. I mean, although we think that those are, and so that same Dr. Sandhya Mishra, whose photo you saw, she went looking, all over, okay, and was able to locate some microalgae, okay, which had reasonable amount of oil. There are, most algae don't have oil, but some do. And this particular two microalgae that she got, I think we had about what? About, I think about 12% oil, roughly. It's not a huge amount. Like Jatropha had, the seeds have about 35% oil. If you take something like groundnut, it has got about 60% oil. Okay. So there are compared to that, 12% oil is nothing, but still, it was important because it would be another source. Okay. So this is one example where you may have seen things like this. Okay. Or if you have not seen, at least go looking for them next time you go somewhere. Like you'll find sometimes in the waters. Okay. This was, of course, somewhere uh, in some one of the coastal look. I think it was in Diu or some place like that. Uh, and so you have this kind of algae which form mats, you know. Okay, and it's amazing. I mean, you can literally lift off that mat. You can see this guy lifting off the mat from the water, you know, and then you basically try and extract the oil, from this mat. Okay, that was one approach, and the other, of course, was actually growing in a controlled manner, relatively controlled. Uh, but it's the second one which became more popular. Okay, and again, just like I showed you for Jatropha biodiesel, this is the first experiment in the world, where a car was run on marine microalgal biodiesel. Okay, and this is all data. All these reports are international reports. They're not our reports. Okay. All right. In fact, the former chief minister of Maharashtra, Mr. Vilasrao Deshmukh, you can see him pouring the microalgal biodiesel into this car. It was a Tavera Ford car. No, General Motors. Oh yeah, General Motors, because we were working with General Motors at the time. Yeah, and one was, you grow those mats. The other is that, like for example, there are many, like in Vadala, you'll find that quite a bit of salt is produced. Okay, so you grow salt in salt pans. Okay, so actually you can bring in seawater into those pans, and then you can inoculate with your microbes, which can grow. Okay, so they're actually being raised with seawater, and then finally, when the microalgae have grown sufficiently and under certain temperature conditions, they tend to settle at the bottom. Okay, this particular algae was chlorella. Okay, but chlorella is very well known, but there are hundreds of varieties of chlorella, and what Dr. Sanjay Mishra was found is the one which had the highest oil content, and let me tell you that there were something like at one time about 14 laboratories all across India involved in this kind of a project. And so these things settle down. Then you dry the biomass, you harvest it. Okay, and then from that, using more or less the same technology as what I showed you for Jatropha biodiesel, is not very different. Only thing is that this oil has phospholipid, so you have to take out the phospholipid. But once the phospholipid is taken out, the rest of the process is identical. So you can actually make the biodiesel, and this is what Mr. Vilasrao Deshmukh is putting. And it's interesting. You can see this correspondent who was riding in this car, while it was in Delhi. This correspondent took a test ride in the Tavera that was flagged off by the minister. The experience was equivalent to that of any other diesel vehicle, accompanied by a monotonous hum by a diesel engine. The 2-kilometer drive around the central secretariat area was smooth and without any hiccups. Okay, so I mean, and so when you are making a product, make sure that you are making a product which is worthy, of actually being fed into an engine or whatever. Otherwise, if you go and spoil the car engine, nobody will look at you the second time. Okay, so always err on the side of safety. Be very, very cautious. Test it out. Be 100% sure that you have got everything right, and then only, you go and do these kinds of things. Okay, and yeah, so I told you about the oil. Yeah, well, you can see, I mean, typically the chlorella gave about say around 11 to 11.5% of oil, maybe we didn't recover all of it. Maybe there was about recovery was about 70-80%. So probably it had about 14-15% of oil, and this is the amount that we could extract out. Okay. So, and the other very important thing, remember, uh, oil, fuel is always a very cheap thing. Okay. So it doesn't cost like gold. So you have to, just like in the Jatropha case, you saw that everything was converted into a useful product. So here also, after you take out the oil, the rest of the microalgae algal biomass, you can recover all kinds of things from it. Okay, amino acids, this, that, name it. Okay, and so always make sure that you are making the best use of your biomass, because biomass is very precious. Okay, and so you must make the best use of it. Okay, and just like in the case of Jatropha, this is the analysis of the biodiesel from chlorella oil. Okay, more or less comparable properties, except that the phosphorus content was uh, quite high. Okay. And that's why it's so important to know all this. Like I can see, in fact, I'm noticing just now that this was marginally higher than the 4 ppm. Like let's say here, or phosphorus content. You remember 4 ppm max? Okay. So to that extent, there was a marginal deviation which I noticed just now. Okay. But didn't seem to make much of a difference. Okay. Now, I will also pass on, especially I prepared this for the mechanical engineers, because you all will be more interested in the engine end, and I will send you this paper, it's published in Energy Conversion and Management, where regular diesel, Jatropha biodiesel, and the microalgal biodiesel were compared, under different modes of operation of a standard engine. Okay, urban mode, rural mode, in a motorway. Okay, those kinds of modes, and effectively the conclusion was that their performances were quite comparable. And downstream, there is no issue if you want to make biodiesel. There's absolutely no problem. Upstream is the problem. Raising those millions of tons of biomass has turned out to be a far more difficult problem than one imagines. And this is what, if some of you are working, and especially those who are into life sciences, you might want to have a look at. Where are there opportunities to grow these things? Maybe in hilltops or wherever. I told you that you can also use the vegetable oil for running aeroplanes. Okay, and now this kind of biodiesel is different from whatever I showed you. What I showed you was the methyl esters, or ethyl esters. Okay. Now, one of the things is that those kinds of esters, they have a point of a cloud point which is around maybe around -2 degrees centigrade. Okay, so after that, minus 2, and we work with some companies like Bama Lorry, and maybe we were able to uh, uh, reduce that to something like -8 degrees centigrade or so. So up to about -8 degrees centigrade, you might be able to manage with that kind of methyl ester, but when you are working with an aeroplane, at that height, okay, of 40,000 feet, okay, where the temperature is minus 40 degrees centigrade, that thing will become like a solid, okay, that fuel. So those methyl esters will not work, right, in these kinds of applications. Okay, of course, I mean, there are so many applications like trucks and this that, I mean, you can the bulk of the applications you can do with the normal methyl esters, but if someone says I want to run an aeroplane, then you have to start looking at a different approach. And we did talk about this before, what is known as hydro treating of vegetable and algal oils. Okay, they are what? They are again just triglycerides. Okay, uh, now over here, what you do is that again you have to split this. Okay, you need to split it so that you get these fatty acids. Okay, and the glycerol can be taken out. Okay, but that's not all. What you have to do is that you have to make some chemical changes, in this structure. Okay, so for example, this is a typical triglyceride. There will be some olefinic bonds, which gives you iodine value. Okay, and these are your ester linkages, whatever we discussed. Now, the technologies that typically are used, okay, to make the kind of fuel that will be suitable, let's say, in an aeroplane, that is done by this hydro treatment process. So one of those is that see if you can remove the carboxylic group. So this would be like a decarboxylation. Okay, so I'm doing what? I'm just converting this into CO2 and I'm getting RH, right? That's what I've done. Now, you could also, in the presence of hydrogen, you can carry out a reaction, similar reaction, where again you'll get RH. Okay? Because you're doing it under a reducing environment with hydrogen, you will not get carbon dioxide, right? You will end up getting carbon monoxide and water. And this, then you can do what is known as a water gas shift reaction, okay, and where it forms CO2 and liberates more hydrogen. So that's how you can increase the amount of hydrogen that you can get for this particular process. Okay, so this is known as decarboxylation and decarbonylation. Okay, because in one case I effectively just took out the carbonyl. Okay, this is CO, carbonyl group, and or decarboxylation CO2 group. Okay, then you can also have other reactions like hydrodeoxygenation. So all of these are done with hydrogen except for this first one. Okay? And you can see over here what you're doing is that you are actually reducing the carboxylic acid group into a CH3 group. Okay, so you have got RCH3. That means you've got one extra carbon. This carbon is now CH3. Okay, so that's what this is. Okay, then what you can also do is, what has been found is that if you have straight chain molecules like this, they tend to solidify more easily. Like for example, if you take paraffin wax, that it solidifies, right? You get a wax. Okay? But when you introduce a lot of side chains, branching, okay, then what happens is that that same hydrocarbon now will remain like in a liquid form, okay, at a much lower temperature. Okay, and so what you have to do is introduce that kind of branching, and that is done through this process of hydroisomerization. That's what you're doing. Okay. Now, And why do I need hydrogen? Because when I am introducing branches, okay, I will require hydrogen for that. Okay, so that's where the hydrogen gets consumed, and also some of the olefins, etc. You might want to saturate, okay, with hydrogen. Now, it could also be that if your chain length is too long, like for example, suppose I've got here and I have to crack it, that means I have to break it and make it smaller. Okay, so that could be known as a hydrocracking, right? So I take this, isomerized stuff, and I might want to now split it into smaller molecules. Okay, and usually the smaller the molecule, the lower will be the freezing point, and so this is the kind of structuring, which is done to be able to make this the fuel for this kind of application. They start with the same feedstock, Jatropha and algae, okay, but they end up doing something different in terms of the final chemistry. This chemistry is quite different from transesterification chemistry. Okay. Is that clear to everyone? Okay, so with that, actually, we come to the end of biomass. Okay, so we are through with biomass, and now the next few lectures will be on solar energy. Okay, and so now what I'll do is that maybe I'll just maybe introduce the subject. Okay, and we will continue with the next class on Thursday. Now, I have told you, I showed you this before, that actually the sunlight, which we receive on Earth, okay, is basically it's like as if it's a black body of around 5,800 degree Kelvin temperature from the surface of the Earth, radiating, and when it radiates, and I showed you earlier the equation, which basically determines what will be the relative intensities at different wavelengths. Okay, which I will maybe I'll in the next class I'll again show you, or you can go and look at your lecture. And what we also said is that this is how it comes out when there is no atmosphere. But when there is atmosphere, okay, then the atmosphere tends to absorb some of the radiation, and so there is a drop in the intensity. Okay, and after that also, the atmosphere will have different kinds of impurities, like water molecules, carbon dioxide, okay, unburnt hydrocarbons, okay, all kinds of things which are there today in our atmosphere. Our air is not pure nitrogen and oxygen, there's a lot of junk in it, okay? And those things can absorb parts of the radiation, so where it absorbs the radiation, obviously the solar intensity there will become zero, or will drop significantly. Okay, and so finally, what you'll be left with is a plot which looks with all these bumps. It'll look something like this. Okay, the green stuff, that is your final solar energy. Okay, and this is the same solar energy which plants were using for their photosynthesis, and which you will use in all your solar energy applications. Okay. Now, there is another thing which is important to note, and this is the basic plot. I mean, not the only one. But there was another plot, but this is what one of the people got the Nobel prizes this time for. In physics. and it was for atmospheric physics, and where they were able to show the what will happen if CO2 builds up. Okay, and they also did a very nice solar radiation balance. And let me ask you the question: this solar radiation is keeping on falling on Earth. So what's happening with the solar radiation? What's happening? Where does it end up? You can imagine the amount of solar energy falling on Earth, and if it had to continuously keep, and it's been going on for God knows billions of years, then the Earth would have been unbearable, because every day, every second, you can imagine how much of energy is falling. But what happens actually is something very, very interesting. Okay. Uh, Now, look at this value over here. All right, 342. And this is the watts per meter. Okay, watts per meter. 342 watts per meter. Okay, and that means per second, so many joules are basically coming per square meter, of the surface of the Earth. Okay, now 342. Okay, now if you have your calculator, I want some of you all to just do some addition subtractions. Okay, now typically some of this radiation, solar energy as it comes, okay, it actually interacts with the atmospheric gases. Okay, and so part of it gets diverted here. Okay, and later on, maybe part of it will be changed and part of it will be unchanged, but these actually get reflected back into space. So it doesn't really end up on Earth. It will finally end up in space. Okay, now the rest of it is getting absorbed by the surface of the Earth. Okay, this is the thing. Okay, now from here also, uh, some amount which got it's getting reflected, again from the surface of the Earth. Okay, roughly about 30 watt per meter squared. Okay, so this 30 and this 77, which was interacting with the clouds, it becomes 107. This is the 107 which is going off into space over here. Okay, now the rest of it got absorbed. Now some of it is actually getting converted into thermal energy, and so it's generating heat. Now thermal energy means it's all at a longer wavelength. Okay, now another thing that happens is roughly about 50% of the total radiation that falls on Earth, okay, it actually goes into the evaporation of water from the seas and rivers. Okay, that's how our clouds etc. are being formed. Okay, all that heat is being used, into evaporating water, and it is forming clouds. And later on, when it rains, it's releasing that latent heat. Okay, and when it releases the latent heat, the that will be again a longer wavelength energy. Okay, and so those are all the things which are also leading, but we'll see what happens. Okay, then there is things which are being radiated by the surface. It's not evaporative, but it's just being radiated, from the surface. Okay, that's this stuff. Okay, and there are greenhouse gases, which are again heating up, and they are again heating up the surface. Okay, you can see these figures, 324 watt per meter squared. So if you were to now do an analysis, now finally all of this stuff is exiting from the atmosphere. Okay, it's all coming out from here. All right, but it is coming out at a longer wavelength, and because of these longer wavelength, heated up stuff that are being formed, so that's why there is an increase in the temperature that is taking place. Okay, that's what the greenhouse gases, etc., are doing. Now if you add it up, just see uh, how much is, um, one second. We have got, uh, yeah, you add up 235 and 107. How much is it?
342, sir.
Yeah.
342.
So you can see this is the same 342. Okay. So finally, everything that the sun gave us is actually being reflected back into space, but some of it is reflected back in exactly the same wavelength distribution, this, as was coming in, and some of it is having a distortion, of the wavelengths. All right, and it is of a longer wavelength, and it is getting radiated into space. Okay, similarly, I'm not going to do it here. You can do a heat balance for all of this and see which is correlating with which. You'll find that every number will be perfectly matched. Okay, and this is basically the entire thing that happens with solar energy, and what actually led to this time's Nobel Prize. Okay, so I thought I'll especially tell you about this, since this year the Nobel Prize was given for this. I don't know if I have already put it in your Google Classroom. If not, this 1965 article written by Manabe, all right? I'll probably also put it. Those who are interested, in those kinds of things, you might want to read it and see if you can understand it. Okay. Now, I will also introduce just one more term. Okay, and then we will close today. Okay. Now you can see it's written AM0, AM1.5, AM1.5 global, AM1.5 direct. Okay. So let me just explain to you what is this AM 1.5 and this that. Okay. Now, this AM is if, for example, my solar radiation were falling, if the sun was on the zenith, and if it is falling vertically, right? All right, then this is the shortest distance from the sun to the surface. But if, let's say, because the solar radiation is falling everywhere, so if it is falling at an angle, then it will create a hypotenuse, and this length will be longer. Okay, so the intensities tend to change, depending on the path length through which the solar radiation is traveling. Okay, and AM basically is L by L0. Okay, so for a path length through the atmosphere and solar radiation incident at angle relative to the normal to the Earth's surface, the air mass coefficient AM is equal to L by L0, where L0 is the path length at zenith, that is normal to the Earth's surface, okay, and at sea level. And the air mass number is thus dependent on the sun's elevation path through the sky. Okay, and it varies with the season it varies with the time of day, and it varies with the latitude. Now, these things we will be covering in one of the subsequent lectures. When I show you how exactly the sun and earth are traveling with respect to each other, and what exactly happens, to the solar radiation. Okay. So remember that. Okay. And atmospheric conditions considered for standard reference spectrum at AM 1.5 hour. Okay. And so even if you have AM 1.5, you might have a place, you might have two places with AM 1.5 the same, but the atmosphere in those places could be different. Okay. So they also define what kind of atmosphere is considered as the standard reference atmosphere. Okay. And that is that the precipitable water vapor, in other words, the relative humidity of the air, it will have 14.2 mm of water vapor out of the 760. Total ozone is 3.54 because ozone can absorb UV radiation. Okay. And the turbidity, because the turbidity can scatter radiation. Okay. Whenever you have got turbidity, what is considered as direct radiation. Okay. When there is no turbidity, and when you have turbidity, it will scatter. Okay. So more the turbidity, more the scattering, and less the direct radiation which is falling on the sun, and what you will end up getting is more diffuse radiation. Okay. So AM0, now let's look at these numbers. AM0, the spectrum outside the atmosphere, approximated by 5800 Kelvin black body. All right, that is AM0. Okay. Where is it important? Like if you are buying a solar cell, okay, and you have to ask people, hey, tell me what is the AM0 specification or rating for the solar cell. Where is it important? In communication satellites, because they are in space, they are not in our atmosphere. Okay. So over there, I have to consider this particular value, AM0, and this is AM0. Okay. So you know what is the kind of radiation that is available in space. AM1, the spectrum after traveling through the atmosphere to sea level with the sun directly overhead is referred to as AM1. Okay. In other words, when it is vertically falling, okay, from the zenith, okay, that is AM1. And AM 1.5, as I told you, is basically at an angle, you know, and typically why AM 1.5 is important, it says many of the world's major population centers and hence solar installations and industry across Europe, China, Japan, the United States of America, and elsewhere, including northern India, southern Africa, and Australia, lie in temperate latitudes. AM 1.5 is thus used commonly for reference standards in these places. Okay, so that is the relationship between the solar spectrum as you see it on Earth and at different places on Earth. Okay, and you can see that these are quite different. Okay, all of these, and so this is what you need to take into account. Okay, and this is the radiation that we will be basing all our subsequent solar energy related lectures on.